Alright, so I'm going to try a new technique with these videos where I actually present my written solutions for these, well, written as in latexed, typesetted, wherever the adjective is for me used LaTeX to write stuff and then put it on computer screen. So, I think that'll be a little easier for me because I can go faster through some of the solutions without having to really slow down to take time to write everything out, and I can spend more time. I don't know, I think it'll be more time efficient. Okay, so we have this problem. So we're going to let lambda be a partition of n, and we write it as in this way. So we write 1 a few times, 2 a few times, etc. So basically, for an example of what this looks like, if you have 1, 2, 2, this is a partition of 5 because 1 plus 2 plus 2 equals 5. And this is written where you put the 1s first, then the 2s, etc. And then and of course I include this whenever I type up an algebra assignment and I have to index things by the natural numbers. I always make sure to specify that 0 is not included because I'm an analyst and that's the convention that I like to use. Anyways, so the LIs are the number of times each index appears. So in this particular example for this partition of 5, L1 is 1 and L2 is 2. And then if you sum them all up, you're going to get n. Yeah, because 1 times 1 plus 2 times 2 is 5. So we want to prove that this formula down below here is the number of elements in the conjugacy class of Sn of cycle type lambda. So basically, that's because the conjugacy classes in Sn are determined by the cycle types if you write an element as a disjoint cycle or a disjoint union of cycles. And we've talked about this before, how these are precisely the conjugacy classes. So, anyways, and of course we think of these conjugacy classes as partitions by considering the cycle types. So for example, if we consider all things of the form like a 2 cycle and then a 3 cycle, A, B, C, D, E. These are disjoints. So a 2 cycle and then a 3 cycle in, say, S5. Then this corresponds to the partition 2, 3 of 5. And of course in that scenario, L2 is 1 and L3 is 1. So that's how you identify those two things, the partitions of n and the way of writing an element as a disjoint union of cycles. Anyways, so let's suppose that we have some element of Sn and its cycle type is lambda. So each index between 1 and n is going to appear in exactly one cycle of sigma because we are assuming that we have written it as a product of disjoint cycles. So each index must appear. It must appear only once. And so there are n factorial possible ways of writing sigma, but just because you write sigma in 2 different ways doesn't mean you've come up with different permutations. So if you take 1, 2, 3, 4, 5, this is the exact same thing as 2, 1, 3, 4, 5. This is really what we're doing in this problem, is we're really accounting for all of these different ways of writing these elements of Sn. And so of course we start with n factorial, and then we have to divide by some number that's going to account for these adjustments we can make to sigma while maintaining adjustments you can make to the way that you write sigma, but still maintain the value that it takes as an element of Sn. So, all right. So anyways, so for example, if you have, if you fix some particular index n, this should be an I. I know I made this issue earlier I made this mistake earlier in this write-up. There were some times where I had written n when I meant to do I. This is another one that I didn't catch. So for some I in the natural numbers, then for any I cycle, writing it in these different ways gives you the same exact thing. It doesn't matter which one. If the I cycle goes from A1 through AI, it doesn't matter which one you write first, so long as you go in order, increasing the index by 1, and then after AI, looping back to A1, you're going to get the same thing. And so if you have a particular I cycle, the number of ways of writing it is, well, let's look at these indices here. We have A1, A2, all the way up through AI. And so you've got I different possibilities here. And of course, if you were to keep going from here, the next thing that comes after this is just A1, comma, blah, blah, blah. But that's exactly what we started with. And so this is a complete list. And so therefore, if we count these, we've got I cycles. So for every single I cycle we have, we must divide the number of choices for sigma by I to account for the equivalent ways of writing each I cycle. So in particular, since sigma contains Li I cycles, by the definition of that's what Li is, we must divide the number of choices, which was n factorial, by I to the power of Li. And we must do this for every single I. All right, so that's that. So that's sort of where this part comes from. Furthermore, since the I cycles are disjoint, reordering these cycles has no impact on the value of sigma. And so we know that there are Li I cycles, and so there are Li factorial possible ways of reordering these I cycles. And then to account for these reorderings, we must divide the number of choices for sigma by I. I think this should be Li factorial. Right, because that's what we're doing here. There are Li factorial possible orderings, and so to account for these reorderings, we must divide by Li factorial. So, therefore, for every single... again... for every single I, we must divide the number of choices for sigma by this thing, because we've divided, the first thing we said that we have to divide by I to the Li, and now we've shown that we have to divide by Li factorial. And so, once we do this for every single I in the natural numbers, we have our final number of possible choices for sigma, and it's given by this formula. So therefore, and this is exactly the formula that we wanted to prove was the number of possible choices for sigma. And so therefore we have arrived at our final answer, and this completes our proof.